The man in the picture is Terence Tao. He is considered to be one of the greatest, if not the greatest, living mathematician. In 1988, he took part in the International Mathematical Olympiad. The competition took place in Australia and lasted 2 days, July 15 and July 16. Terence Tao won the gold medal that year, at the age of 12. He perfectly solved 5 of the 6 problems of the competition. From that year until now, he is the youngest winner of a gold medal at the International Mathematical Olympiad. But he could not solve the problem number 6. This is the problem of which we will see the solution in this video. The problem was so difficult that Arthur Engel said, and I quote, "Nobody of the 6 members of the Australian Problem Committee could solve it." Before jumping to the problem, let me tell you something about the proof. One of the ideas of the proof is the technique known as Vieta Jumping, which essentially consists of a proof by contradiction in which you suppose that there is a solution to an equation, then you take a minimal solution, and then you prove that exists a smaller solution, and therefore you get a contradiction. Okay, having said that, let's look at the problem and its proof. The problem is the following. Let a and b be 2 positive integers such that a times b plus 1 divides a squared plus b squared. Show that a squared plus b squared over a times b plus 1 is a perfect square. Let's get into the proof. I want to show that for all a and b in N such that ab plus 1 divides a squared plus b squared, we get that a squared plus b squared over ab plus 1 is a perfect square. Okay, let k be a natural number such that k is not a perfect square. If I prove that for all a and b in N such that ab plus 1 divides a squared plus b squared, we get that a squared plus b squared over ab plus 1 is not equal to k, then I solve the problem because for the arbitrarity of k, I get that this number is not equal to every other natural number which is not a perfect square. Thus, this must be a perfect square, and I solved the problem. Suppose now by contradiction that you can find a and b in N such that ab plus 1 divides a squared plus b squared and a squared plus b squared over ab plus 1 is equal to k. Then, if you consider the set S of all the a plus b such that a, b are natural numbers and a squared plus b squared over ab plus 1 is equal to k, you get that this set is non-empty because of the fact that you supposed that 2 numbers such that exist. So, since the set is non-empty, you can consider its minimum. Let's call it M, capital M. Since this minimum exists, we can find capital A and capital B in N such that A plus B is equal to M and a squared plus b squared over ab plus 1 is equal to k. Without loss of generality, we can suppose that capital A is bigger than or equal to capital B. We can do that because since a and b are 2 natural numbers, one of them is greater than or equal to the other. So I'm just saying that the one which is greater than or equal to the other is A. Okay, now from this we get that a squared plus b squared is equal to k times ab plus 1. And so we get that a squared plus b squared minus k times b times a minus k is equal to 0. Consider now the equation of variable x squared minus x times k times b plus b squared minus k equal to 0, and call this first member, this polynomial, p of x. Okay. Now, since a is a square of this equation, so since a is such that p of a is equal to 0, we know that the other root of this equation, which we can denote with c, is a real number, because this is a polynomial of degree 2. So if a root is a real number, then also the other must be. Okay, so let's call c in R such that p of c is equal to 0, the other root. Since a and c are two roots of this polynomial of degree 2, we know that we can decompose the polynomial in this way. We can write p of x as x minus a times x minus c. So we must have that x squared minus xkb plus b squared minus k is equal to x squared minus a times a plus c times x plus a times c. Then, by the fact that these two polynomials must be equal, we know that the coefficients must be equal. So we know that minus kb must be equal to minus a plus c, so we can change the sign, and b squared minus k is equal to a times c. Okay, so from the first equation we get that c is equal to k times b minus a, and thus c is an integer, because these numbers are all natural numbers. From the second one, we get that c is equal to b squared minus k over a, and thus c is not 0, because we know that k is not a perfect square, and thus k cannot be equal to b squared. Thus we got that c is an integer which is not 0. Okay. Given that c is a root of the equation, we know that c squared minus c times k times b plus b squared minus k is equal to 0. So c squared plus b squared is equal to k times cb plus 1. Okay, but now the first side of this equation is greater than 0, since b is greater than 0. And in reality also c squared is greater than 0. Then k is greater than 0 because it is a natural number, and so we get that cb plus 1 is greater than 0. Thus cb is greater than minus 1, but since these are integers, we know that this means that cb is greater than or equal to 0. But we know that c and b are not 0, both of them, and so we get that cb is greater than 0. But b is greater than 0, it is a natural number, so we can simplify it, and we get that c is greater than 0. So we have proved that the other root of the equation is a natural number. But from this, we know that c squared plus b squared over cb plus 1 is equal to k, And we also know that C is equal to B squared minus K over A from this, remember that. And from this we get that this is less than or equal to A squared minus K over A, because we supposed that A is bigger than or equal to 0, to B. But this is A minus K over A, and this is less than A, strictly less than A, since K and A are bigger than 0. So we have found that C plus B is in the set S, and C plus B is strictly less than A plus B, which is equal to the minimum of S, and therefore we got a contradiction. This was everything for this video, and ciao to everyone!